Okay, so we are back. We went through this and we said we apply more VGS, we let up on the squeezing, more current can get through. We apply more VDS, I'm pushing Mr. Amp through harder, more current can get through. Okay, I don't care. We've got 3 regions of operation. In one of them, I don't have enough VGS or VDGD to form a channel on either end. This is cutoff. In one case, I have enough VGS and VGD to form a channel at both ends. This is triode. And in this case, I have enough VGS to form a channel at the gate side. I have not enough VGD to form a channel at the drain side, and I'm in saturation. For our digital circuits, these modes of operation, cutoff is my digital off. Somebody ask questions, talk to me. A triode is my digital on. And saturation is where I use my analog circuits. Okay. These MOSFETs, this is what they give you in CEDRA, are the planar transistors. The way they're building things now, instead of putting the gate on top of the drain, part of the problem is here, is that electrons moving between the source and the drain can move directly underneath the gate. Some of them move through the substrate and back up to the drain. Those generate noise and leakage that we don't like. When they came up with this idea to help them get to these smaller transistors below 20 nanometers, basically the idea is they take the source and drain and they elevate it. It's a lot harder to build. The chemical processes it takes to build this are a lot more difficult, more expensive. But the thing they found is they had a lot better control over the drain source current because it's all flowing directly under the gate and very little of it's flowing through the substrate. There's another idea they threw in here, and it took both of these, these were competing ideas for a while. One manufacturer did the FinFETs, another manufacturer was using fully depleted SOI, and basically they put a very thin layer of oxide all the way across this device, and that blocked the electrons from moving through the substrate because there's an insulating layer right there. To actually get down below 10 nanometers, they had to use both the FinFET, flipping this up and putting it on a fully depleted substrate to control the current of the electrons better. And so they have no more wandering electrons through the substrate. This is on the right is modern processing technology. This is getting to be obsolete. There's still some old processes around. If you don't need to have itty bitty die, sometimes it's cheaper to actually, instead of trying to use the 5 nanometer, the 3 nanometer processes, which are really expensive, sometimes it's a better trade-off to go to a 20 nanometer process that's older and more mature and the factory's already paid off. If you just don't need to get the die size down that small. So there's all these engineering cost benefit analysis trade-offs. The business guys take care of that. The group leads, the management people, they'll figure that out. And when you're a young engineer and kind of just tell you what you're going to do. and they'll do all those calculations for you. But if you learn how to do that, that's something that gets you, like, that's something the managers do. I was always the techie person. Okay, right. Labs start next week, and you do have a pre-lab due. It's in BB Learn. I recommend you look at it before an hour before the lab. We want to talk about, we got 10 minutes left. I'm going to talk about the transistors. Now, from a circuit designer point of view, what happens is I send my die out for fabrication, and 4 or 5, 6 months later, I get it back. It takes a long time to go through all the chemical processes to get down to the end. And when I get my die back, there's a sheet of paper in there that says, okay, this is the process parameters we measured that day. They will tell me things about the thickness of the oxide, or the dielectric strength of the oxide as it was measured on that die on that particular day. There's variations. I go and I put these numbers in my SPICE deck, in my parameters that are modeling what I'm expecting this integrated circuit to do before I ever power it up. I may need epsilon ox, I may need the thickness of the oxide, I want to put that in there. I want to put the mobility in there as it was measured when it came off the line. The C-ox, I can either calculate from these two, or they give me another measurement for that. Kn prime, I'm going to stick that into there, or I calculate it from all those and stick it into my SPICE deck. And then I go and I re-simulate the circuit to make sure that everything's still going to work and I'm not going to burn anything out. And I may fine tweak some of my operating voltages that I'm putting in from the outside world to get them right. All these things are included in the model that you put into your simulation. And a lot of the time of a integrated circuit designer's life is spent in simulation. Because if you're waiting 6 months to get this chip back, if I screw up, it's gonna take me at least another 7, 8 months to get another chip in. So you wanna get it right the first time. And I haven't never built a chip that didn't work. Some of them had features. Some of them had things we had to tweak, voltages on the outside that we had to tweak, or maybe some digital, whatchamacallit, as an example. I one time built a D to A converter that, it was a 5-bit D to A converter. So the digital input pins, 4 of them were active high and 1 of them was active low. We could fix that with programming. But you had to know what you were fixing, right? It's a really weird transfer curve till we figured it out. There was one bubble missing in the whole scheme that caused this. So we were still able to use the chip. We just had to change our programming a little bit. So you make them work once you get them, but you spend a lot of time up front making sure that it works the way you think it's going to before you send it out for processing, because it's expensive and it's time consuming, and time costs money too. So a lot of integrated circuit design is spent in front of a computer doing simulations and making sure that things are going to work, and talking to people and making sure your part of the design will work with the other person's part of the design, and trading specs and things like that. A lot of time spent writing also. So this C-ox is the capacitance per unit area of the oxide. Kn prime equals mu C-ox. This is the process transconductance parameter. It's like the gain of every transistor divided by its size. And so it's good for the whole process. When I look at the individual transistors and I know what their W over L is, I know how big they are, I can calculate the transconductance for that. And it's the Kn that ends up in the current equations. Now this is something, I got 5 minutes. I want to, yeah, okay. Be careful with these. The units are fundamentally going back to centimeters. Mu n has centimeters squared per volt second. So before I do these calculations, I have to make sure the units match up. TOX, I need to put in centimeters. So 4 nanometers is 4 times 10 to the minus 7th centimeters. This is in micrometers. That's 0.18 times 10 to the minus 4 centimeters. I have to convert everything back to centimeters or you'll be off by huge orders of magnitude. So be careful with those calculations. They're straightforward, but they will bite you. So this mobility, mu n, that's of electrons. 100, somewhere between 100 to 450 centimeters squared per volt second. Where does that come from? Mobility is a defined parameter. The velocity of the electrons equals some constant that I define as mu times the electric field. Now velocity is usually in like centimeters per second. Mu, it's a proportionality constant. I don't know what the units are yet. Electric field is how many volts per centimeter have I put across that device. So when I cancel the units out, that's how I end up with centimeters squared per volt second. And so it's just basically telling you how much electric field do I need to get so my electrons moving faster. If I put a higher voltage, a higher electric field, I'm going to get faster moving electrons up to a certain point. Electrons can't move faster than the speed of light, and when they're inside a silicon crystal, they're going to bump into things, which makes them not even being able to get up close to the speed of light. That will be called velocity saturation. I'm almost done. These are transistors. We want to figure out, in order to figure out which region of operation we're in, we have to know something about the relative voltages. VGS, remember, from 280, is just the voltage at the gate minus the voltage at the source. Both of the voltage at the gate is the voltage at the gate relative to ground. VDS would be VD minus VS. So I figure out the voltages at each one of these, I can figure out all the rest. So the gate is always, these are NMOS, and these are PMOS, because these are outies on the top row, and those are innies on the bottom row. This is the gate, the source is the one with the arrow, and the drain is the one without. So if I want to figure out VGS for this transistor, it's VG minus VS, 0.2 minus 0.0, what is 0.2 volts? We've got VGS. If I want to find VDS for that transistor, I just take the drain voltage, 1.3, minus the source voltage, and that gives me 1.3 volts. And if I want to find VGD, that is the, VDS is big, VGD is gate to drain, 0.2 minus 1.3 is negative 1.1 volts. And yes, it is. I'm really amazed with myself sometimes. I'm not going to tell you guys what's going on in my head. Okay. VGS. Okay, no, it's not. So that's an NMOS. For the PMOS, you could go through and figure out each one of these, and these are in the slide solutions, and I'm running out of time, and I don't want to bore you to tears. This is the source, this is the gate, and this is the drain. Notice in this, on the NMOS, the source is on the bottom. In the PMOS, the source is on the top. Just because the higher voltage on the PMOS is on the source, the higher voltage on the NMOS is on the drain. We'll go back and review more about the regions of operation and the current equations on Tuesday. Have a good holiday. You don't have to come to class on Monday, so you can catch up on your homework. Any questions? Please, somebody ask a question. Let's see who showed up. Danielle Dawkins, are you here? Chris, wait. Oh, you're in chat, aren't you? You don't have a microphone.
Her and Chris are both here.
Her and Chris are both here. What about Alex Reesley?
Yeah, I'm here.
Oh, yay. Okay, good. Yes, good, you're back. It's good to see you back, Alex. So homework's due on Tuesday. Homework 1 is pretty much a review homework, but still budget some time for it. Don't wait till the last minute. I will help you and I will answer questions all I can, but I can't do it right before class because I have another class right before class. Okay. All right. I will see you guys. And hopefully we'll have IEEE meetings starting soon in some way, form or another. A lot of them were virtual last semester. We managed to do a few things. Okay.
Thank you.
Okay, I'll see you. Bye, Mouse.
Yeah. Bye. Have a good evening.
I'm sorry if you guys had to hear that comment about mac and cheese earlier.
That's
My
okay. Gabriel, I've heard far worse things when people don't realize their microphone was on.
Thank you. My mom was trying to figure out what she should cook when I come back home. I was like, not that.
Okay.
Thank you. Take care.
Okay, I'll see you. Oh, stop recording.